Okay, so here we go. We're going to combine different elements. And you can see this one is going to have, it's got a spring element, it's got a height change, and it's got some friction. Okay. And so what does it tell us? It tells us about our spring constant. Okay, so we've got that. That's our spring constant. We've got our height change. All right, so our delta H, we're going down. So our height change is negative 1.5 there. And what we're looking for is really this, okay? How far is it going to slide with its friction, okay? And so we begin with our first law of thermodynamics, okay, here. And this time we have to use all the parts. Just like this. So it's going to get kind of messy here when we write it all down. Okay. So you always want to go ahead and write everything out. All right. Don't take shortcuts on this. It will come back to haunt you. Okay. I'm just going to call that L delta H minus 1/2 K. X final squared minus X initial squared minus mu mg delta x final, and delta x final is actually what we're looking for there. Okay. Okay. Well, what can we throw away here? Well, what's the speed we start off with? Well, it's butted up against the spring. Okay, and so it has. You can see here it's got no velocity when it's starting, and the spring is compressed. Initially, it's compressed 0.2. Now, when the spring opens up and it expands outward, it doesn't go all the way to 0. Okay, and that's okay. It doesn't have to completely relax. There's probably something, I mean, we don't know what we're looking at here. There's probably something that stops it. It's like catches. Okay. For example, like in our projectile launchers, they're spring powered, right? The spring in there it's what's called spring. It's called pre-compressed. So it's got just a little bit of tension in it while it's in there. That kind of keeps it from rattling around, and it also keeps it from flying out every time we shoot the ball. Okay, so there could be a variety of reasons for this in terms of our design goals, whatever it is. But it's only going to relax out about 10 centimeters. Okay, just like that. Okay, but it's starting from 0 speed. That's what I'm trying to get to. So V initial is 0. Now, way over here is V final. This is cool because, I mean, we want it to stop. So that means V final is also 0. So this whole side of my equation is actually 0. Okay, just like so. Okay, so now let's rearrange this. I will do this in a couple of steps. All right, instead of just one ginormous step here. But I want to put this term on the other side so I can set it up a little bit better. So I've got mu mg delta x from the friction. Okay, then my minus mu mg delta h minus 1/2 k x final squared minus x initial squared, like this. Okay, and then once I do my algebra on this thing, okay, I'm going to be left with my m's going to cancel in this first term, my g's going to cancel in this first term. So this is kind of weird. I get this kind of odd term delta h over mu. Okay, now that's definitely odd looking, except that delta h has units of meters. Mu is a coefficient. It doesn't have any units. Okay, and so units wise, that kind of works out. Even though it's weird looking, we don't see that kind of thing every day. All right, but that's okay. That's what we got there. Okay, then we've got minus 1/2, and then I'm gonna have k over mu mg, and then all that's still onto x final squared minus x initial squared, like so. Okay, let's throw some numbers in here. I've got minus, and my delta H is actually minus 1.5 meters over mu, which is 0.35, minus a half, 300 newtons per meter. Okay, so that's weird again when I get that thing. I'll show you a trick though. So we got 0.35, and I've got 0.5 times 9.81, and my final position was 0.1, and the initial compression of the spring was 0.2. So we've got this right here. Okay, so let's kind of look at the units here. mg, that's weight, right? I mean, that's weight oftentimes. Well, not oftentimes. It is the weight. So it has units of newtons. Okay, so what I've got right here is newtons. So that's going to cancel out my newton right here. Okay, that cancels out my newton. And then over here, each one of these is meters. I forgot to write it in. So I've got meters squared, but there's a meter down here, my newtons per meter, cancels that guy and leaves me with just meters for the whole thing, which is great because we're looking for a distance. Okay, well, run all this through your calculator, and what you end up getting is 6.91 meters. Okay, and so you'd have to have a pretty long rough patch in order for this thing to come to a stop. All right, it actually comes flying out of there pretty quickly. Okay, so we could go back and we could calculate if we wanted to. We could calculate, what's the speed right here. Maybe call that VA, and then what's the speed once it gets down here, VB. But we don't have to get those. I mean, that's not necessary. We can go start to finish, boom, boom, no problem. We just have to account for everything that happened to it in between those two steps. Okay. All right, there we go. So that's the first one. Okay, I'm calling these Joulapalooza because the units of energy is joules, right? Get it? Joulapalooza. Anyway,